So to wrap up our discussion of the fractional knapsack problem, we need to ask, why is this greedy algorithm working? Hopefully by this point in the class, I've taught you not to trust strange greedy algorithms, right? You should when you see a greedy algorithm or when you think about a greedy approach, your first instinct should be suspicion. You should not expect this thing to work. It should only be by rigorous proof that you actually come to a belief that a greedy algorithm is the right algorithm to use for something. So why is this one working? Well, we're going to build up a proof here. I'm going to show you one technique to prove why this greedy algorithm works. And this technique is slightly generalizable. This is something that you can kind of use this idea for certain kinds of problems, certain kinds of greedy algorithms to show that they give you optimal solutions. All right, so here's the way we're going to structure the argument. Let me sketch the argument first, and then we can actually kind of fill in the details. So I'm going to say that I'm going to specify a feasible solution to the fractional knapsack problem by A. And so what does A do? A says here's A1, A2, dot, 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 all the way up to AN, where each of these A's, each of these AI's is a fraction, right? So each of these AI's says here's the fraction of item I that I'm going to take. So here's a claim. If A, and just to put a marker on it, I'm going to say if some solution A star is optimal, okay, then it contains the first greedy choice. Okay, what do I mean by the first greedy choice? I mean the first thing that the greedy algorithm decided to do. Okay, so if A star is optimal, then A star contains the first greedy choice. Okay, well, being optimal is something that we understand, right? What does optimal mean? It means that it solves the problem with the highest possible value, right? That it is, of all the different possible ways of taking fractions of items, it's one that maximizes the total amount of stuff, of value that we can take. And we also know what this means, right? We know what it means to contain the first greedy choice. The greedy algorithm is a deterministic algorithm, right? It ranks the items by their value per weight, and then it maxes out each one in succession, right? So what does it mean to contain the first greedy choice? Well, this means it maxes out the highest value per weight item. Okay, maxes out highest V per W item. Okay, that's what the first greedy choice does, right? The first thing the greedy algorithm does is it says, what thing gets me the most bang for my buck? Let me take as much of that as I can. Okay, so now looking at this statement, this is like a stepping stone to proving the final thing that we want to prove, right? We want to prove something bigger than this. Actually, we want to prove that if A star is optimal, then everything in A star was selected by the greedy algorithm. But as it turns out, this is all we need, right? If we can just do this, then we can get the rest of the statement essentially for free. Okay, so we're just going to say, if A star is optimal, then we're going to ignore everything else the greedy algorithm does. But let's just ask, or let's just try to prove, is the first thing the greedy algorithm did, is that optimal? Okay, so looking at this, it's hard to see where you would take this, right? This is a fairly large statement. And so let's reformulate it in a way that makes it much easier to think about. Okay, so notice this is an implication, and so let's call this piece here. I should write it like this. Let's call this piece P, and this piece Q. And what we've just done here is we've said, what we want to prove is that P implies Q. So what we're going to do with this proof is we're going to, instead of proving that, we're going to prove the contrapositive. Okay, so if you don't know what contrapositive is, pause the video, go look it up. You have to know what contrapositive means, right? But I'm going to trust that from here on out, you know what contrapositive means. Okay, so the contrapositive is the statement where we reverse the order of the propositions, or if you like, we reverse the causality of the propositions, or we reverse the conditioning of the propositions, and then we negate them. right? So the contrapositive says not Q implies not P. And we know by the rules of propositional logic that these two have the same truth value, right? So if P implies Q, then so does not Q imply not P, right? So these are logically equivalent. All right, so let's focus on this. What is the contrapositive of the above statement? Well, the contrapositive says that if some solution A, and I'm going to call this A tilde, right, just to give it a different name than the one we're talking about above, if A tilde does not contain the first greedy choice, does not contain the first greedy choice, comma, then what? Then A star, or then A tilde is not optimal, right? Then A tilde is not optimal. Okay, so why is this easier to deal with? Well, if you think about the top statement makes us say, let's suppose something is optimal. And we don't really know what that means, right? We just know that it maximizes something. But we don't have like other properties of optimal solutions that we can do something with. Okay? So then it becomes very hard to argue the conclusion. It's very difficult in this one to argue P implies Q. But if I think of not Q, what does not Q mean? Well, not Q just, it gives me an actual property that I can play with. Not Q says if some solution, right, some feasible solution does not contain the first greedy choice, I know exactly what that means, right? That just means that it doesn't max out the highest value per weight item. In other words, in this solution, there's some of the highest value per weight item left over that's not being put into the knapsack. Okay, that's a property that I can actually leverage, which makes it easier to work the proof in this direction. So all I have to do is show that any solution, any feasible solution that doesn't satisfy this property I'm underlining in red somehow is not optimal. Okay, so let's think about this. Okay, so let's suppose that A tilde doesn't contain the first greedy choice, which means that it doesn't max out the highest value per weight item. Okay, so suppose A tilde doesn't max out the highest V per W item. Okay, so let's just call this item I, right? Just for the sake of having something we can name it. So let's suppose this is item I. Okay, so go search the list and then find the index of the one that has the highest value per weight. All right, so let's break this into some cases. So case 1 says the following. Case 1 says, let's suppose that there's empty room in the knapsack. Okay, so in A tilde, the knapsack is not full. Okay, what does this say? Well, if the knapsack is not full, then that means there's some empty room where we could put more stuff. Okay, so the fact that A tilde doesn't max out the highest value per weight item, and there's extra space, means that there is something that we can put into that space, right? What can we put into that space? Well, whatever is remaining, or some of what's remaining of the highest value per weight item that we didn't put in the first place. Okay, so if the knapsack is not full, fill it. I should even say, instead of fill it, I should just say, then add more of item I. And what will this do? This will improve the quality of the solution. This improves quality. Thus, what does that tell us? Well, we've just shown a way that we can do better than A tilde, and that means that A tilde is not optimal, right? So A tilde is not optimal. Now notice we didn't show how to make an optimal. All we showed is that in this case, if A tilde doesn't contain the first greedy choice, then it's not optimal. okay, which was our original goal. If you scroll back just a bit, our original goal was this thing here, and we've just shown in one case that is true, right? If A tilde doesn't contain the first greedy choice, then it's not optimal in the situation that we've described here, where the knapsack isn't full in A tilde. Okay, so there's case 1 is done. All right, what's case 2? Well, case 2 is everything other than case 1. Case 1 said if the knapsack is not full. So case 2 says that in A tilde, the knapsack is full. All right, there's no more room to put extra stuff. Okay, so what do we do in this case? Well, look, if AI, or if item I was not maxed out and the knapsack is full, then what this means is that there's some AI left over. And what we could do is we could take out some of the other stuff, the non-item I stuff in the knapsack, and put in a sliver of AI. And we know that it has a higher value per weight ratio than anything else, so we know we can improve the quality of the solution that way. So just picture it something like this, right? You've got some of item I, and then some of other stuff, other non-I stuff. And then outside the knapsack, you've got more item I, right? So you've got more item I stuff. I. So here's the knapsack on the left. On the right, there's this little tiny pile of item I that's not in the knapsack. Well, how can we take what's in the knapsack and improve the quality of it? Well, it's simple. We just find a sliver that weighs the same as this. We remove that sliver, right? We chuck that, and then we take this item I stuff and we slide it into that spot we created, right? And we know that that'll improve the quality of the solution because, suppose we remove a pound of something. Well, putting back in a pound of item I is guaranteed to give us more value than whatever it was that we removed that wasn't item I, because we know that item I has the highest value per weight of any of the other items. So we know that VI over WI is greater than VK over WK for all K that are not equal to I. Okay? So remove some K, replace it with I, and you improved. Right? What does this mean? Remove some K, replace with I, and better off. Right? What does this tell us? Well, it tells us a procedure that we can follow to improve the quality of A tilde. Right? Improve the total value taken with respect to A tilde. Right? If we can take A tilde and make it better, that means A tilde is not optimal. Okay? So what do we have? Therefore, A tilde is not optimal. All right, what have we proved? Well, we proved that there's, using these two cases, which cover everything, either the knapsack's full or it's not full. In all of those cases, if a solution that is feasible does not contain the first greedy choice, then it is not optimal. Right? So that's this statement here in the blue. Right, we just proved that statement. Okay, now why does this statement tell us the other one? Well, because this statement is the contrapositive of the first thing we wanted to show. Right? Here's the thing that's proved. So now this is true. So now why is this good enough? Right? Why is this good enough? Well, suppose I have a solution that satisfies this. Right? Suppose I can prove this to you. Well, then I can just take this statement and I can repeat it as many times as I want to prove the overall statement. Right? What's the overall statement? That if the greedy algorithm begins optimal, that it'll stay optimal. Right? And so here, this says that the greedy algorithm is guaranteed to begin optimal. Okay? So then what do? We say, well, suppose we've just run one step of the greedy algorithm. What it did is it maxed out the highest value per weight item and gave us something that is at least a partially optimal solution. And now let's look at what's remaining of the problem. Well, now we have some capacity left, and we have some items left. Well, if I tell you a capacity and I tell you items, that's a knapsack problem. So now we just run the greedy algorithm again. We pretend now that's another problem, a new problem, run the greedy algorithm again, and what do? Well, we see here that the first thing the greedy algorithm does has to be optimal for that subproblem. So then we can just string these together several times and say, well, we know now every time we run another step of the greedy algorithm, it's doing something optimal for the problem that is remaining. So as long as it began optimal, which this proves, then it's optimal all the way to the end. Okay. So then we can essentially use this argument as many times as necessary, if you like, to give us the final conclusion at the end of the problem. Okay. So that's why this greedy algorithm is optimal for this problem. And this argument can generalize to other kinds of optimization problems, which happen to have an optimal greedy algorithm.